All right, welcome to our last lesson on permutations and combinations. So this is um, maybe the toughest part. I think people generally can do okay when we see things in bits and pieces, but when you have to put it all together, then it can get a little bit confusing. So let's just review what we know. Okay, so we know that we can use the fundamental counting principle when there are multiple decisions to be made. Okay, so um, if I'm choosing digits for a number or if I'm putting people in line for a photograph, we multiply the number of choices at each decision point together, and we want to always consider the restrictions first. Okay, so if it's a number that has to be even, you want to make sure you go to that last digit and make sure that's even and then place the other ones. Factorials are used when we are placing all objects and order matters. So if I have 7 people and I need to put them in a line, all 7 of them, then I could say 7 factorial. So it's kind of a very specific situation. We use permutations when order matters, and we use combinations when order does not matter. Okay, so permutations, that's the NPR, and combinations is NCR. Okay, it's important to note that permutations and the fundamental counting principle, you can use either of those. The fundamental counting principle can be used every time you could use a permutation. So basically, the question you have to always ask yourself is, does order matter? Are there restrictions? And then go from there. Okay, so let's just go through some examples. The first one says there are 26 people in a FM30 class. You want to select people. How many different selections are possible if you need 5 people to form a group to work together on classroom decorations? So you ask yourself, does it matter what order I select the people in, right? So do they have specific jobs? No, they're just all going to be decorating the classroom. So it doesn't matter what order it is. So that means that it is a combination question. Okay, so if order does not matter, it's combination. And it is going to be the total that I have to select from, combination 5. And that gives me 65,780 different groups of people that I could form to work together, which is kind of crazy when you think about it. If I need 5 people to have very specific jobs, and those jobs are chalkboard eraser, paper hander outer, hole punch queen, the stapler dude, and the pencil picker upper. Well, if I have very specific jobs, well, it's different if you are the chalkboard eraser than if you are the hole punch queen, right? So that is then a permutation. So we could do it as 26p5. And when we put that into our calculator, we get 7,893,600 different. Okay. Important to note, you could also do that as there's a spot for my chalkboard eraser, my paper hander outer, my hole punch queen, my stapler dude, and my pencil picker upper. And I have 26 people that can go there, and then 25 and 24, 23, 22. Okay, so this just goes to show that the fundamental counting principle is the same as a permutation. Number 2, you are selecting classes for next year. You plan to take ELA, physics and chemistry. If there are 5 different ELA teachers, 3 different physics teachers, and 2 different chemistry teachers, how many different combinations of teachers could you have? Okay, we need to make 3 different decisions, right? And there are kind of stipulations. I need to choose a ELA teacher, a physics teacher, and a chemistry teacher. So there are 5 different ELA teachers, 3 different physics teachers, and 2 different chemistry teachers. So that comes out to be 30 different combinations of teachers that I could have. Okay, how many different 6-card cribbage hands could you be dealt if A, there are no restrictions? So we have to ask ourselves, does order matter? Does it matter what order the cards come to me? And the answer is no. So this is a combination question. So if I'm dealing from a standard deck of cards, I have 52 cards, and I need to choose any 6 because if there's no restrictions, so 52C6 gives me 203, so 20,358,520. If all of your cards are red, well, that then means that I am still choosing 6 cards, but I'm only going to pick from the red ones. So 26, choose 6, gives me 230,230 different hands that I could get there. Okay, so if there's restrictions in a combination, it's usually just reducing the number that you have to choose from. How many different ways can 9 cars be lined up on a car lot for display? So, I mean, you could do one, like I'm making decisions. Which card am I going to put first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth? So I have 9 to choose from, then 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1. You can do that. You might recognize it as there's 9 and I'm placing all 9, so it would be 9 factorial. You might also recognize it as order matters because when I put them in a different spot, that's different. So 9p9. All of those will give you the exact same answer. And sometimes that causes confusion for people because there's 3 different ways to think about that question. But no matter what, you get 362,880. Okay, so there are tons for you to practice here. Always ask yourself, does order matter? And do I have to worry about any kind of a stipulation?